Hello, let's continue with our calculus optimization problems. The fifth problem in the list is this. A right circular cylinder is inscribed in a sphere of radius r. Find the largest possible surface area of such a cylinder. For those who are unfamiliar with the adjectives right circular as applied to a cylinder, circular means that the two bases, the top and the bottom, are both circles. And in the first illustration, this one, those two bases are not aligned with each other. If they are, then you get our usual cylinder. And that's what we refer to technically as a right circular cylinder. But when we use the term cylinder, it's mostly a right circular cylinder that we're referring to. But its formal name, I suppose, is that right circular cylinder. So, okay, we want its largest possible surface area. Now, the only thing that's stopping us from arbitrarily increasing the height and the radius of the cylinder is that it has to fit inside a sphere of given radius small r. Now small r decides how big the sphere is going to be and therefore how big the cylinder with largest surface area is supposed to be. So we call small r, in this case, a parameter. It's a mathematical term that's used to refer to a quantity which is fixed, and so therefore all other quantities are to be expressed in terms of this parameter small r. Now, inside this sphere in blue, shown at the bottom of shown below the problem statement, you could inscribe many cylinders, one of which is shown here in red. So the dimensions of such a cylinder would be its radius and its height. The radius of the cylinder, I've denoted it by small x. That's a radius that's different from the radius of the sphere given by the parameter small r. Many such cylinders are possible. You could make the value of small x smaller, so that would make the cylinder thinner. Consequently, it would be taller. Or you could make the radius small x of the red cylinder larger, but then consequently its height would be shorter. So we're looking for just the right radius small x in order for the surface area to be as large as possible. Now the other dimension that we need for our red cylinder is its height, and that height is going to be double the dimension that I'm tracing with my cursor, which is part of a right triangle whose hypotenuse is small r, being traced by my mouse, and the other dimension is small x. Therefore, half the height of the cylinder is going to be the square root of, hold on, that's going to be the square root of r squared minus x squared. So therefore, the surface area of our cylinder, s as a function of x, is double the circular base area, so 2 times pi x squared, plus the lateral side of the cylinder, as mentioned in the previous problem. You could think of that as the area of a rectangular sheet that's wrapped around the cylinder, whose height would be double the square root of r squared minus x squared. And then the other dimension of the rectangle wrapped around the side of the cylinder would be the distance around the circumference of the top circular base, and that circumference is 2 pi x. So times 2 pi x. So this is our surface area, and this is what we want to maximize. We're trying to find the largest possible surface area. Let's clean this up a bit. You have 2 pi x squared, and then plus 4 pi x, and then the square root of r squared minus x squared. In case you're wondering, of course, for the radius of the red cylinder, you could have chosen, as long as it's not small r, you could have chosen, let's say, big R. But then when you're dealing with the parameter and the variable, sometimes it could get so confusing. We're more accustomed to using small x for the variable, so that's why I decided to use small x here. Of course, you can still use big R. You just have to keep track which one is the parameter and which one is the changing variable. So big R is the variable. Now, one of the next things we have to do is to identify the domain, because at the end, after we arrive at the critical numbers, we're not supposed to stop there. We're supposed to justify that the critical number is not useless, that it actually produces the absolute maximum or the absolute minimum. And knowing the domain can help you determine the justification that you're supposed to make. For example, would you have to use the first derivative test or the second derivative test? If the domain is a closed interval, you could use the extreme value theorem, which means you just have to evaluate the function at the endpoints and at any surviving critical number. And in that case, because you're using the EVT, you wouldn't have to use, there would be no need to use the first or the second derivative tests. Now, what then are the possible values of x? So if you go back to the figure, as I trace x, clearly it cannot go beyond the radius small r of the sphere, and neither can it be negative, so that means small x is at least 0 and at most r. All right. Well, of course, practically, we're not thinking of small x as actually becoming 0 or small r, but it helps if it is possible to include the endpoints. So we have a closed interval so that all we have to do is use the extreme value theorem and not have to use the first or second derivative test. All right, so the domain of S is, as already indicated up here, the closed interval with endpoint 0 and r. So for the critical number, we need, of course, the derivative s prime of x. You have 4 pi x. And then for this, you're going to have to use the product rule. So let's take 4 pi x as one of the factors. Its derivative is 4 pi. And then we copy the radical, the square root of r squared minus x squared. Next, we copy 4 pi x, and then the derivative of the radical, so that's going to be a 2 downstairs, and the square root of r minus x squared also going down, and then the derivative of r squared minus x squared is negative 2x. All right, so here's what we have. You could clean this up a bit. I see 4 pi is a common factor. All right, just algebra your way through this. 4 pi is a common factor, and then you have three terms. I'm going to combine all of them under the same denominator. That would have to be, after canceling this 2 here, this 2, and that 2, then the denominator is really now just going to be the square root of r squared minus x squared. Don't forget that you've already factored out 4 pi. So here you have x times the radical, square root of r squared minus x squared. And then from the second term, 4 pi has been factored out. So you're left with just r squared minus x squared. Two square roots multiply to each other. And then followed by, this time it's going to be minus. 4 pi has been taken out. You still have x squared in the numerator. Yeah, that's what's going to be left. It's just minus x squared now. All right. So now, do not forget that there are two types of critical numbers, those which make the derivative 0 and those which make the derivative undefined. So uh, if s prime of x does not exist, the only way that's going to happen is if the denominator is 0, and that's only going to happen when x is equal to small r, which happens to be one of the endpoints. So it turns out there's nothing new so far to be added to the evaluations. And next, when s prime of x is equal to 0, that means this numerator here would have to be 0. So you're looking at the equation x times the square root of r squared minus x squared, and then plus r squared minus 2x squared is equal to 0. And then what you have to do is you have to solve for x here. What I would suggest is the non-radical part, this one, double underlined, move that to the right side. So then you would have x times the square root of r squared minus x squared, and then that's going to be equal to 2x squared minus r squared. And for you to be able to remove the radical, you would have to square both sides. All right. I would like you to try out the algebra on your own. All right, because I only have 15 minutes for this YouTube video. But then once you square both sides, then you would have no radical. You would have a fourth degree polynomial in x. This is what you're going to end up having. It's going to be 5, so dot 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 5x to the fourth, all right, minus 5 r squared x squared, and then plus r to the fourth power is equal to 0. Even though it's not exactly quadratic because x is raised to the fourth power, you could treat this as a quadratic function in x squared so that you could still use the quadratic formula x squared. After the quadratic formula, all right, I encourage you to fill in the details. This is going to end up becoming 5 r squared plus or minus, all right, the square root of 5 times r squared all over 10. All right, so two possible values for x squared. In the end, we have to find the value of x, but then because x is positive, all right, then when you take the square root of the whole thing, you only take, well, the principal square root of 5 plus or minus the square root of 5 over 10. And then I factor it out, r squared. After you take the square root, you could just take it out as r. So that gives us two critical numbers. All right, so all you got to do now is evaluate the surface area function at our two critical numbers. So you got to evaluate s at first the square root of 5 plus the square root of 5 over 10, and then r. Please do the algebra. This should give you exactly 1 plus the square root of 5 times pi r squared, and then s at, yikes, the square root of 5 minus the square root of 5 over 10 times r. That's going to be exactly, if I did this correctly, 5 plus 3 the square root of 5 over 5, and then pi r squared. And then you have s at 0. S of 0 is 0, and s of r is 2 pi r squared. Now it's just an issue of determining which is the largest. All right. So all of them have a coefficient of pi r squared, and this, after calculator work, turns out to be 2.342. No need to multiply to pi because all the four values here are multiples of pi r squared, and then 1 plus the square root of 5 is 3.236, which means you get the absolute maximum when x is equal to the square root of 5 plus the square root of 5 over 10 r. All right. So that means to maximize the surface area, the cylinder should have radius equal to the radius small r of the sphere multiplied by this particular radical crazy expression, 5 plus square root of 5 over 10. Bye-bye. Thank you.